Forces in action at a distance. Gravity, electricity, magnetism. Why? Who knows? But how? On Science Without Walls. At a distance. Forces reach out through space and cause an effect. Two objects or bodies separated by some distance feel the presence of each other through space. Gravity isn't the only such force. Two others you are highly dependent on are electricity and magnetism. Let's relax and return to our physicists in the wild fantasy. Let's ask if there were other things you observed there, other questions you asked, which appear to be basic. Let's assume it's a very dry summer night in Utah. You're in a dark cave. It's a bit chilly. You have furs and hides. You've also used fibers from plants to make textiles, clothes, maybe even rugs. At night, in the dark, crawling into that primitive sleeping bag, you experience a form of private lightning. Pretty startling. And today, in the dark, while dressing or under the sheets, you also experience these little sparks. Micro-lightning, static electricity. You've seen and maybe even experienced large-scale lightning at close hand. You also have combs. You see hair, fibers attracted to your comb. You think that your local micro-lightning, the comb, and the sky's macro-lightning could be related. Back to the real world. It's party time. Balloons. We've all done this, played with a static charge on balloons. If you rub a balloon in Utah's dry climate, it'll attach to the wall. If it's not rubbed, it won't stick. It falls. Now take two balloons, unrubbed, hanging from thin threads. Stroke each one with a piece of fur. As soon as the second one is stroked, they repel each other. Bring the fur back up to one of them. It attracts fur. Is this unique to fur and the rubber from which balloons are made? This is a glass rod. Rub it with a piece of silk and now bring it close to the fur-rubbed balloon. Wow, attraction. The fur-rubbed balloon is our reference point, our instrument, our detector. By rubbing the balloon with the fur, let's assume we gave it a negative charge. Let's say we transferred electrons from the fur to the balloon. So both balloons now have electrons, negatively charged particles. And since like charges repel, the balloons repel each other. The balloons are sensing charge. We can call them an electroscope, from the words electron and scope, a kind of instrument. Now, if something attracts the balloons, since we know that unlike charges attract, we'll assume that whatever does the attracting is positive. If something repels the balloon, then we'll assume that it has the same charge as the balloon. That's negative. So our physicists in the wild, and a lot of other wild physicists over the centuries, have arranged materials in what scientists and engineers call a triboelectric series. Tribo is a word for rubbing or friction. Stuff at the top of the chart develops a more negative charge than stuff lower down if the two are rubbed against each other. Utahns are all experts at private lightning because much of Utah is among the driest places on the planet. The amount of water vapor in our atmosphere, in our air, most of the year, is very low. It turns out that when something is charged, it can become discharged quickly through a very thin film of water. Water is a conductor of electricity, although not a very good one. So if the air, the humidity, is high, these static electricity experiments aren't so dramatic, like on the East Coast or in the South, where it's humid almost all the time. In Utah and throughout the Southwest, if you shuffle your shoes across the rug, and if the shoes and the rug are of the appropriate materials, the friction transfers charge from one to the other. You can end up being highly charged, and when you approach a metal doorknob, the charge suddenly jumps across the gap just before you touch it. You feel a shock of static electricity, either jumping away or towards you, depending on the charges and materials involved. You've just been struck by private lightning. For the charges to jump that half centimeter through dry air, which is very typical in Utah, there was a voltage difference between you and the doorknob of some 5,000 volts. Now, if we had any doubts that any of this was connected with lightning, Ben Franklin put that to rest in a very hazardous experiment, which he fortunately survived over 200 years ago. Franklin coined the terms positive and negative in his description of electricity. He used kites and rods to demonstrate that lightning is nothing more than the discharge of electricity on a grand scale. Don't try this because it was a very dangerous experiment, and Franklin and his family were very lucky that he survived it. Lightning is nothing to play with. But small-scale static charge, or triboelectricity, is really easy to observe, especially here in Utah. You sense it, feel it, often. Look for it, enjoy it. Our physicists in the wild also examined rocks and minerals and came across a special mineral they called lodestone. It's actually quite common. Here's one from Iron Springs, Utah, near Cedar City. Well, an ancient physicist took a sliver of one of these, floated it on some water, and found that it oriented itself north and south. And no matter how they would try to disorient it or force it, when they released it, it would line up north and south. This action seemed to have nothing to do with gravity and nothing to do with inertia, and had nothing to do with static charge. This was something different, and they called it magnetism. The floating magnet was a primitive compass, pointing north and south. They quickly figured out how to mount it so they didn't have to carry around a cup of water. They quickly realized that it was very useful. They could navigate with it, particularly during the daytime and on cloudy nights when they couldn't navigate by stars. So one of my very old ancestors, a Portuguese named Ferdinand Magellan, used such compasses, together with star navigation, to basically sail around the world, thereby conclusively proving, as if anyone at that time had much of a doubt anymore, that the world was round. But that's another story. So we have electrical forces from fur, textiles, balloons, and from lodestone we have magnetic forces. Our ancient physicist ancestors developed an easy way to visualize those magnetic forces. And rather than use the lodestone now, which is a weak magnet, we'll use a stronger magnet, like the ones you've used in elementary and high school. These two magnets obviously repel, and they obviously attract. They feel each other over very large distances. Here's a thin box. We have a magnet below. We sprinkle iron powder on the top. The powder lines up. Why? Well, we all know compasses point north and south, and presumably these filings are lining up in some sort of magnetic force field. We can map that magnetic force direction with a cute little three-dimensional compass called a Magna Probe. It's a small bar magnet mounted on low-friction bearings, so it can orient in almost any direction. We bring it close to the strong magnet, the probe orients. The orientation or direction of the magnetic field mapped out by the iron filings is exactly what we see with this little probe. These little compasses can also work as probes. So because of these experiences with iron filings and magnets, those early physicists started talking about magnetic lines of force. The little iron particles obviously experienced a force, and they obviously organized themselves in a pattern, mapping lines of force. The magnets somehow produced a field, something in space at a distance, which could act on, could disturb that iron-like material or other magnets placed in that field. The magnet's effect on empty space is caused by a field. The iron powder maps or provides an image of that field. This huge piece of natural lodestone at the Utah Museum of Natural History shows magnetic lines of force on a grand scale. Once we think in terms of lines of magnetic force, we can extend that concept to electrical attraction and repulsion. We say there are electrical fields and lines of electric force which extend out in space from charged objects, like our charged balloons or fur or bed sheets. There's a standard way of drawing these lines of force for both magnets and for charged balloons. Magnets have north and south poles. Forces come in pairs, like action-reaction and attraction-repulsion. So magnetism needs a pair of poles. We assume the lines start at the north pole of the magnet and return to the south pole of the magnet. Charge is treated similarly. Although electricity is usually the flow and movement of electrons, negative charge, in the early days of electricity, it was considered the movement of positive charge. Lines of electric force are normally shown leaving a positive charge and returning via a negative charge. Although you can have charges separated, as we saw with our balloon electroscopes, if you have too much separated charge, the force of attraction between those groups of unlike charges becomes so great that the excess electrons actually jump the gap and discharge, as with lightning and with the micro-lightning you experience on a doorknob after dancing across the rug. So unlike charges tend to be balanced, at least eventually. Whenever you have one kind of charge, you tend to have the other. That's why the so-called electric lines of force are viewed as starting from one group of charges and ending on another group of unlike charges. Electric lines of force are also called electric fields, and magnetic lines of force are called magnetic fields. Physicists also talk about conservation of charge. Unlike charges tend to eventually cancel out, and the system becomes neutral. As you'll see in a few minutes, moving charges produce both electric and magnetic fields, which can move through space like waves, and these are called electromagnetic waves. Light is one form of electromagnetic wave. Radio stations broadcast another form called radio frequency electromagnetic waves. Unlike sound waves, which need air in which to travel, electromagnetic waves can travel through space, just as light travels from the stars through space to Earth. The electric and magnetic forces are there, whether or not there is air. They are not like waves on a string or in water or a sound wave in air. Those things simply don't happen if you take the air away or the string away or the water away. So like gravity, electricity and magnetism is able to exert its forces through space. Electricity didn't start to become useful until a constant and reliable source of it was developed. Van de Graaff developed a generator. As you crank it and move the belt, you cause a separation of charge by friction, just as we did by rubbing the balloons. If you allow that charge to flow to you, then you become charged. And that means the individual hairs on your head become charged and repel each other, so they stick straight up. Later, with the development of chemistry and the availability of metals like zinc and copper, batteries were made, and they are very reliable sources of electric charge. You know that a battery has two poles, a positive and a negative. And sometimes it doesn't matter how you hook it up, and other times it matters a great deal. It depends on the specific circuit and what you are trying to do with the difference in potential or voltage between those two poles on the battery. A simple way to see that batteries are doing something is to take one, a small one like this 9-volt battery, and touch it to your tongue. There's a tiny shock and tingle due mainly to chemical reactions occurring at the positive and negative poles. Don't do this with anything over a 9-volt battery, and don't ever do it with anything that is even indirectly plugged into the wall. Batteries, the common batteries that we use every day, AA, C, D, and the 9-volt transistor radio battery, are all low-voltage, direct current, DC, sources of electricity. And because of their small size and low voltage, little current is drawn from them. But alternating current, AC electricity, at 110 volts, under the right conditions, can deliver very large amounts of current. And that current can readily cause your heart's natural pacemaker and muscle to malfunction, causing heart failure and death. So never mess with electricity, especially AC electricity, unless you know exactly what you're doing. The nice thing about a 9-volt battery is that both poles or connectors are on one end. When you touch that 9-volt battery to your tongue, you're actually moving electricity through the salt water on the surface of your tongue, stimulating various sensations which you feel as a minor or major discomfort. You're also doing electrochemistry with the salt, sodium chloride, in the solution. You even produce a little chlorine gas, which is not pleasant. With very little salt in the solution, the battery mainly causes the breakdown of water into hydrogen and oxygen molecules, which bubble away from each electrode. Don't do this for more than a few seconds because you'll discharge and ruin your battery. Wash it off to get rid of the salt, dry it, and it should still be good. We can use electrical energy to break apart water molecules into their hydrogen and oxygen components, thereby transforming electrical energy to a form of chemical energy. It takes about 1.2 volts to break up the water molecule, forming oxygen and hydrogen, which can then recombine together spontaneously to form water. We can recombine them under controlled and safe conditions, transforming the chemical energy of hydrogen and oxygen to heat and water. There's rapid progress being made in the application of hydrogen as a clean fuel, as a substitute for oil and gasoline. Utah's Leonardo on Wheels Traveling Science Center has ping-pong pinball, in which you manually make electricity, use it to make hydrogen and oxygen, and under controlled conditions, ignite and burn the two gases to launch a ping-pong ball, showing that it takes work to separate water, but it reforms easily, releasing lots of energy.
On fire. You go. On fire.
With batteries, we can do other experiments. Metals conduct electricity. Non-metals do not. Light a light bulb with a battery, connect a wire and bulb using different kinds of materials. Some allow the light bulb to light and others don't. Those that allow electricity to flow are called conductors, and those that don't are non-conductors or insulators. Materials tend to fall into two groups, conductors and non-conductors. It's easy to keep the electricity in the conducting wire by surrounding the wire with a non-conductor, which serves as a shield. There's no way for the electricity to get out through that shield. It has to run down the wire. With insulated wires, we can connect all kinds of things together and make circuits, bells, motors, gadgets. There are some particularly macho electrical types who like to work with large currents, like the kind that can come from your car battery. Your car battery is large and heavy and delivers 12 volts. This big jumper cable is coming from my car battery. It's insulated. We've arranged to have it go through this white cardboard for this experiment. Here are some small compasses near the wire. They're on the white cardboard so you can see them. Now we connect the other end of the wire through a 12-volt light for resistance and connect that to the other pole on the battery, letting current flow. The instant we make that connection, the compasses respond. Reverse the connection, the compasses point the other way. Amazing. We know that compasses respond to magnetic fields, so there must be a magnetic field around that wire. Electricity and magnetism appeared to be two completely independent, unconnected phenomena until this experiment. Real creativity, really great advances in science, in understanding, are made when you take two different things and look at them in a new light, from a new perspective, and see that they are related or connected. And that's exactly what happened to electricity and magnetism. Electricity produces magnetism. Interesting. Well, Joseph Henry and Michael Faraday apparently had artistic tendencies or qualities because they asked, could there be a natural symmetry or relationship between these two phenomena? If electricity in motion can induce magnetism, wouldn't it be cool if magnetism in motion could induce or produce electricity? A crazy question and a brilliant hypothesis. We'll continue that story next time. For now, respect AC electricity, experiment with low-voltage batteries and with magnets, and experience your own private lightning. Get charged. See you next time.
The thunder rolls and the lightning strikes. Another love grows cold on a sleepless night as the storm blows on out of control. Deep in her heart, the thunder rolls. She's waiting by the window when he pulls into the drive. She rushes out to hold him, thankful he's alive. But on the wind and rain, a strange new perfume blows, and the lightning flashes in her eyes, and he knows that she knows, and the thunder rolls, and the thunder rolls. Thunder rolls and the lightning strikes. Another love grows cold on a sleepless night as the storm blows on out of control. Deep in her heart, the thunder